So this is going to continue our pH lecture, and the important thing to do here, depending on which chemistry class you're in, you'll just want to fast forward until we get to something that doesn't look familiar, because depending on whether you're first period or fourth period, we're in slightly different spots. So keep that in mind here as we start the lecture, is depending on where you got this may or may not be familiar. So your job is to just fast forward to where things don't look familiar. Oakley dokley. So the first thing that I wanted to reiterate is that when you were doing our POH activity and filling in those tables with H plus and OH minus, you were actually doing something rather brilliant without knowing it at the time. What you were doing is you were doing something called a logarithm. And what I'd like you to be doing is taking these notes on the back of your POH packet. There should be a blank, full blank sheet of paper. So that's where we're going to talk about these notes. But just to review, a logarithm, it's something you've normally associated just with math class, but a logarithm has to do with the power. So the logarithm of a number is the power to which the number 10 must be raised to equal that number. So the logarithm of a number is the power to which 10 must be raised in order to equal that number. And again, all of these things that we're talking about today, so pH, we're going to be talking about pOH, hydrogen concentration, and hydroxide concentration are all related to this logarithm idea. Now, just as a reminder, we haven't yet really delved into why we care about H plus and OH minus. Just for now, know that they're going to be important. We're going to actually tackle this next class as to why we specifically care about those two components. And then just remember, anytime you see brackets, we're talking about a concentration in molarity. So when you see hydroxide ions in brackets, we're talking about the molarity of hydroxide ions, or the concentration of hydroxide ions. So the first place we're going to start is with pH. This is the concept that we're all most familiar with. pH actually stands for the potential of hydrogen. Specifically, it's a measurement of hydrogen in a substance. And what you hopefully found out today is that there's a relationship between the pH value and actually the exponent related to how much hydrogen, specifically hydrogen ions, H plus something has. So remember how I said at the beginning that you were being rather brilliant by doing logarithms in your head, even though you weren't realizing it at the time? Officially, the formula that we're going to use is pH is equal to the negative log of our H plus concentration. pH is equal to the negative log of our H plus concentration. One of the things that you're going to be assumed that you know how to do is work these problems on your calculator. So if you don't know where the log button is yet, take time to find it. Depending on which kind of calculator you have, it can be in slightly different spots. But now that we have this formula, it's a pretty straightforward kind of plug and chug is what I call it. You plug the numbers into your answer, you chug it through your calculator, and you get the pH. So let's say we have a problem where our H plus concentration is equal to 1.36 times 10 to the negative second molarity. So this might seem like kind of a tiny number, but actually with regards to H plus concentrations, this is pretty big. A -2 really isn't that small. If you remember, it's 0.0136. So it's actually a pretty big number considering how small we could get. So if I gave you this information and said, what's the pH value of a solution with this? What you would do is you would take the negative log of 0.0136, and then you would plug that through your calculator. And when we do that, you should get a number. Well, if you don't take the negative, initially you'll get a number of negative 1 1.87. But remember, we're taking the negative of that, so that would actually negate the negative. A negative of a negative is a positive. So we'd end up with a pH value of 1.87. For sig figs on these kind of problems, we're going to treat it like we always have in terms of multiplication. So you're going to just look and see how many sig figs are in the number you start with. 0.0136 has 3 significant figures. And so that would be how many sig figs we could keep in our pH. And so remember, like I said, 1.87, that's a low pH. We're talking about something that's very acidic. So even though this initial number isn't very large, the pH that we end up with is actually pretty significant in that it's very acidic. So the next part is to how to do the opposite of these kind of calculations. If you look on your calculator, when you look for the opposite of a logarithm, the answer is actually hidden on your calculator. It's the second function of the log button on your calculator. So if you look at that up, you should see that it's 10 to the x. And so what that means is that if instead of going from H plus to pH, we wanted to go the other way around, say I gave you a pH value and wanted to know the hydrogen ion concentration, the formula is using this relationship 10 to the x, and it looks like this. If we wanted to know the molarity, right, because that's what these brackets mean, if I wanted to know the molarity of a hydrogen ion concentration, I would take the number 10 and raise it to the negative pH power. So again, let's look at an example. If I gave you a solution that had a pH of, let's make this basic, so let's do like 11.3, and I said, okay, find the H plus value. You would plug it into your calculator as 10 to the negative 11.3, and you're not going to stop there. You're actually going to find me the answer. So let's plug that in now. So plug that in, and it looks like our H plus concentration is going to be equal to 5.01 times 10 to the negative 12th. So this is very small, which what we would expect is because when you have a pH of 11.3, you're not going to have much H plus floating around. This is very basic. And we'll learn soon what the H plus has to do with how acidic something is, but for now, just know that 5.01 times 10 to the negative 12th would be our final answer. Now I know to cut it off at 5.01 because 11.3 has 3 significant figures, and so my final answer should also have 3 significant figures. So this is half of it. If you remember though, up here at the top, I talked about 4 different values. We looked at pH, and we looked at H plus. Now we saw how these are related using this formula here, and then this formula down here. But there are these also 2 other values. There's pOH and then hydroxide concentration. And these 2 are actually related in a very, very similar way to how pH and H plus are related. So I'd like you to go ahead and divvy your notes in half here. Woo! And we'll actually look at the pOH over here. So just as pH stands for the potential of hydrogen, pOH stands for the potential of hydroxide, or OH minus. So you can think about pH as a measurement of how basic something is, or sorry, pH is a measurement of how acidic something is. pOH is really a measurement of how basic something is. We tend to use the pH scale more commonly, but they're kind of mirror images of each other in that regard. So let's take a looky-loo. The formulas are going to be almost identical. So over here, we saw that the pH equals the negative log of the H plus concentration. The pOH formula will look almost identical. Instead of the negative log of H plus, it's going to look like the negative log of our hydroxide concentration. So they'll be almost identical. In other words, anywhere you see an H over on this side, you'll plug in an OH over on this side. So again, let's try a practice problem just to make sure that we got it here. let's say I give you a hydroxide concentration of, let's make it pretty big again, because we'll be talking about something that's very basic. Let's say 0.15 molarity. And I said, okay, what's the pOH value? Okay, so you go to your calculator, and remember, it's the negative log of 0.15, which would give us a pOH value of 0.83. Oops, sorry, 0.82. And again, I keep two significant figures here because I have 2 in my initial answer. So that 0.82 actually means that this thing is very basic. So we're talking about something that has a very, very high pH, but a low pOH, and we'll look at why that is here in just a moment. But for now, I just want you to get comfortable kind of using these formulas and working with your calculator. Okay, so just as pOH and pH have these two formulas, we can go backwards in the similar way. Remember how we talked about how the opposite of a logarithm is taking something to 10 to the x power? Same kind of deal over here. If we want to find the hydroxide concentration, we take something times 10 to the negative pOH value. And again, same kind of deal. So let's pretend that we have something where the pOH, let's make this a high number this time. Let's say we have, actually strike that, let's do a low number, 3.26 as our pOH value. And I say, okay, what is the hydroxide concentration? 10 to the negative 3.26. So we take a moment, plug it into your calculator. And again, remember, you're going to use the second function option, 10 to the negative 3.26. And we get a value where our hydroxide concentration equals 5.50 times 10 to the negative 4th. And again, 5.50, this has 3 significant figures because 3.26 has 3 significant figures. And then we'll stick a molarity there on the end. So these are how these numbers are related. They are pretty darn similar in that their equations kind of mirror each other. But remember that pOH is a measure of the hydroxide, which is a measurement of basicity or how basic something is. pH, or the potential of hydrogen, is really a measure of how acidic something is. So we're going to be flipping back and forth between these, and just know that in any solution, when one of these is big, the other one will be small. So I zoomed out here to show you the very last formula that I wanted to give you. And that is, again, you may or may not have stumbled across this during class, depending on how far you got in the green packet today. But the very final relationship that we're looking at actually relates pH and pOH together. And hopefully you discovered that pH plus pOH equals 14 when you add them together. And here's how to think about it, is that these two numbers, when one is big, the other one will always be small. So when we're talking about something that's an acid, we're going to be talking about something that has a low pH and a high pOH. But here's the thing you have to remember. Remember that when we say a low pH value, we're not necessarily talking about a small pH value. We just mean that the number is low. The number is 1, 2, 3. That doesn't necessarily mean that it's weak or not very strong. So another way to think about it, when you have a low pH, they're kind of opposites. You're going to have a high H+ concentration. And then the opposite is same true down here. When you're talking about a high pOH, you're actually talking about a low hydroxide concentration. The flip side is also true, so let's make sure we get that down. When we're talking about something that's a base, we're talking about something that has a high pH, which equates to a low H+ concentration. because remember, we're talking about logarithms, so the relationship isn't exactly linear. When we're talking about something with a low pOH, we're actually talking about something with a very high hydroxide concentration. So the very last thing I wanted to do was preview for you and go through the different ways that we can use these formulas kind of all together. And I'm going to show you 2 practice problems. There are several correct ways to get to the right answers in this one, but I want to make sure that we're comfortable with using these formulas. Okay, so let's consider practice problem number 1 down here. We've practiced with these 4 formulas, one here, one here, one here, and one here. And we've all done kind of the basic calculations that each one involve. But what we're going to look at now is when we have to combine more than one. So take a gander down here. Let's say we're in a situation when we know that the hydroxide concentration of something is equal to 8.1 times 10 to the negative 5th molarity. So we're talking about something that's kind of in the middle, neither strongly acidic nor strongly basic. And I want to know what the pH value is. So the good news is that we have a couple of equations where hydroxide shows up. The bad news is that we don't have an equation that goes directly from hydroxide into pH. So what we're going to need to do is we're going to need to solve this problem kind of stepwise. So if you take a look, we're given a hydroxide value. If you look at the 4 equations that we have so far, only one of them uses hydroxide to get to a different number. And that's this one. We're not going to talk about this one down here because that would give us hydroxide if we had pOH, but we're not there. We're given hydroxide, and we actually need to use it to find another value. So we're going to use this formula up here. We know that the negative log of our hydroxide is equal to pOH, so that's where we're going to go. That's kind of the only thing that we can do with this number at this point. So we're going to say that the negative log of 8.1 times 10 to the negative 5th molarity. And that's going to give us our pOH value. So let's go ahead and do that. So we know, again, find your calculators. The other thing I should say too is that you should be practicing kind of as we're going along, because you're going to need to know how to do this on your calculator. And depending on what kind of calculator you have, it can be a very different experience for you. So just make sure that you know how to do these problems on your own calculator. All right, we got 2 sig figs and 8.1, which means my pOH value is 4.1. But again, I'm not done because ultimately the question was asking for pH. So here we're given a pOH value, and I know I'm getting towards the bottom of the page here. I'll scooch up here in a second. But we know we're given a pOH value. I want to get to pH. Well, looky here, we have a formula that relates pH and pOH. So I could find the pH value by subtracting 4.1 from 14. So I'm going to go ahead and do that now. 14 minus 4.1 equals 9.9 is my pH value. So that was an example of a problem where we had to use 2 different equations to get to our answer because there wasn't a straight shot. Okay, zoomed out one more time. And the last thing that we're going to do is do one more problem, just to make sure we got the hang of it. This time, if I gave you a pOH value, let's say of 12, and I wanted you to find the hydroxide concentration. Same kind of thing again, where I'm giving you a number, but there's no direct route from one problem to the other. So here's what we know. We know that pOH, this one right up here, pOH plus pH equals 14. So that's actually going to be where I'm going to start. I ultimately want to get to H+, but if I can find pH, that'll get me really, really close. So I'll go 14 minus 12, which is our pOH value, equals 2. And 2 is our pH. We know from then this equation right up here that our pH, oops, sorry, I actually want to use this equation right here. We have a pH value. I want to solve for H+, so I'm going to take 10 to the negative 2, and that equals my hydroxide concentration. You plug that out, that's going to be 1.001 molarity. Just kidding. We just need 1 0 there. There we go. Okay, so again, an example of how you need to use two types of equations to actually get to your final answer. Okay, so this basically concludes the pH part of the lecture. So once you have all this, you are good to go.